It means that if you took mass m and transmuted it all into energy, that energy would be equal to the mass times the speed of light squared.
What does that mean?
It means that if you try hard enough, you can break down matter into energy, and that formula tells you how much energy you get out of that matter.
So if I were to take my mass and multiply it by the speed of light squared, I would know how much energy I could possibly have.
Yes, but that would come at the cost of literally obliterating your entire mass into just energy.
No different.
Yeah, I did.
No cotton. They broke the mold.
Alright, Galactus.
155.
How y'all doing today?
It's Friday.
It is Friday. And we're gonna, at least in my opinion, talk about something interesting this Friday. There's only one real thing, there's only one main thing on the agenda today. So if we get through it, I'm not opposed to talking about redstone engineering, but I have to get through the syllabus first. One main thing on the agenda today, if we get through it quickly, we can head on to our weekends. Any questions before we get started, either serious or otherwise? Yes?
What are you gonna get for Halloween?
I usually dress up as Shaggy from Scooby-Doo. My hair is longer than it's meant to be for that purpose this year, but my hair's been about the right length and I can do the voice, and so I just wear a green shirt and cook hot dogs at my church event in character.
You have a dog?
I do have dogs, neither of them look like Scooby. Scooby's supposed to be a Great Dane and he really doesn't even look like a Great Dane, but he's also too dang big. So, I'm not gonna bring either of my dogs to go interact with a bunch of people. I just have a stuffed Scooby that I set next to my mystery machine.
3.3 feet.
That can't be right.
However, it is estimated that Scooby has a height of around 3.3 feet when measured from his shoulders.
Wow.
Oh, his shoulders. Okay, standing on all fours maybe, but if he's on his hind legs like he is sometimes, he comes up to like Shaggy's head. And Shaggy's like 6 foot. That has nothing to do with this class, so that will not be on the test. Yes.
Speaking of the test, isn't that next week?
It's not next week. Let's look at a calendar.
It better not be. I don't think that's correct.
Don't blame me. I thought it was just the week before.
So this week
So
is November. Nope, this is October. What am I saying?
I wish it was.
I wish it was.
Pardon. Today is October 27th. We are wrapping up chapter 7 this week, but that's really just the first of 2 weeks of rotation. So we're still doing rotating things next week for what is officially designated as chapter 8 in terms of your homework. So this week was chapter 7. Next week, the 30th through the 3rd, is chapter 8, rotation part 2. Week after that is chapter 9, which is a little bit of information on pressure and buoyancy. It's not going to be a long chapter, so we should comfortably finish it within that week with enough time to review for the test, which will take place the week of the 13th through the 17th. It'll take place over the week like the first one did. You'll come in during lab to do it, and that means lecture will be review time. And the idea is we get it done and over with so that I can give it back to you graded on the 20th, and then you don't have to think about it over Thanksgiving. Does that sound fair?
Yes.
So when we get back from Thanksgiving, November 27th through December 1st, we'll talk about one last little bit on how waves and sound works, and then enter entirely test review, exam review territory. Exam is this week, but test 2 is this week, 13th through 17th. There will once again be a practice test for it. We will spend lecture time that week reviewing for it. Just answer the question, and does anyone have any thoughts or worries about any of that?
The final test is during finals week, right?
Yes. For this course, there are 2 tests, which are mid-semester, include material up to that point. And then separate from that is the final exam, which takes place during exam season. Does that answer the question? Okay.
What's the average of the final?
Like-
Typically? Like.
Oh, usually around 75. I can load up the previous course's grades and average them real fast.
I mean, you don't have to, I was just wondering, like, how hard it is.
Well, I consider it to just be both tests lumped together in terms of difficulty and length. Exam, you can average this. I taught this course literally a year ago, so I have their averages to look at. Last year when I taught this course, their average was 87 on the exam. So that's actually higher than I remember. I can also look at their test 2 average real quick, if you'd like. Test 2 average, that one was 75.
Oh.
So people do better on the final than they do on the test usually. Yes.
Do we have a date set for our final?
Good question. The school sets aside certain time slots for certain periods, and there are 3 periods for this class this semester, those being C, E, and F. Now, kind of like how all my labs are identical, and therefore you can attend any lab or any test day, my exams are all identical, which means as long as you show up for one of the periods, you're fine. So those 3 pre-scheduled periods for this class are C period, Thursday, December 7th, F period, Friday, December 8th, 8:30 a.m., and that same day for E period, 5:30 p.m. You don't necessarily have to attend the letter you're in. For example, this is C lecture. You don't have to come to this one. You have the option of C, F, or E. So those are the 3 pre-scheduled options to take the exam for this course. Given that that's approaching, I'm actually going to write them on the sideboard there where they will remain till the end of the course.
Honestly, to get out.
So, exam, end of semester. Attend any one of these 3, and they will be written over there until those days come. As for test 2, that will be this week. And like last time, you can take it any lab day that week. Lab meets every day except Thursday. Thursday the 16th does not exist.
Tuesday is not.
It's a myth. Thursday's a myth. Yes?
Do you not like multiple choice? Because technically you can show the work and then like if the answer matches.
Then how is he gonna get
Exactly.
partial credit? He has no partial credit.
I'm not against it though.
I like the partial credit idea.
Well, I give partial credit for everything he's right.
Exactly.
But you can get partial credit for the answers too. Not if you have multiple choice.
I'm not inherently opposed to multiple choice. It's just when I took it at this school, the tests weren't multiple choice, and so that's just the way I built the course.
But you have the power now.
So you're tired.
You can change
There is a bit of a cycle there.
Maybe-
It's important to dismantle cycles that are not beneficial to humanity.
That is true.
That is true.
Fight it against the pre-established order.
Generational curses. We're breaking generational curses.
Now, this is primarily a math-based course, so I would have to do some looking into whether or not the merit of multiple choice for the answers is worth it on the math questions. Technically, there's one multiple choice question, that one with the picking the laws of motion. That's kind of multiple choice. That's fair. That's fair.
Look at A, B, C, or D.
It's not currently in the cards. It might be something I research for future courses, but
say
I will ponder that. Just because it hasn't been done doesn't mean it can't. Thank you for acknowledging that. As of this moment, I didn't have any plans for it, sorry.
Yeah.
As a reminder though, there is partial credit for everything you write, even if it's not math. I want you to tell me what you know, even in paragraph form. Does that help at all?
Yeah.
Okay. Does that answer the question for right now? Okay. Anything else on your minds for the moment? All right. So let's wrap up chapter 7 today. Remember how during this week we've talked a bit about centripetal force and how some real existing force has to play the part of centripetal force to cause an object to orbit some other point. And we brought up the example of the moon orbiting the Earth. What force acts as centripetal force in this scenario? Gravity, very good. Now, how would you go about calculating the force of gravity the Earth exerts on the moon? Historically, how have we gone about calculating force of gravity?
Math times acceleration.
Mass times, specifically the acceleration of gravity, true. And so that would involve Fg equals mass in kilograms times g, whereas g is defined as negative 9.8 meters per second squared. We've used that to find the weight of every object on planet Earth for the entire semester. The problem with that statement is on planet Earth. Is the moon on planet Earth?
Yeah.
No, it's our closest neighbor, but it's not on the planet, which is good because that would mess up the gravity and the tides perpetually. This number has some big caveats. This is only the acceleration caused by gravity on Earth's surface. Frankly, this number changes if you stand on too tall of a mountain, or even if you go too far underground. Because this number very specifically requires that you be a specific distance from the center of the Earth. Weirdly, that number can actually change depending on what part of Earth's surface you stand on. You don't even have to change elevation that much if the type of material under you changes dramatically. So, we've talked about how, centripetal force works on the moon. However, if we were to actually try to calculate the moon's orbit, we would need a different way to find the gravity that the Earth exerts on the moon. In order to do that, we have to talk more about what gravity is as a whole and not just what it means for our lives on planet Earth. So, the main thing we're covering today is something referred to as the universal law of gravitation. Up till now, this has been all we've needed for gravity, but this is not really the definition of gravity. This is just a tool that we use to figure out the force of gravity from Earth on objects sitting on Earth's surface. But that is not the extent of gravity. because Earth's gravity acts on things that aren't on Earth's surface, and there's gravity between loads of things that aren't the Earth. The sun exerts gravity on Earth, Earth exerts gravity on the moon and the sun, and there's loads of things in space that exert gravity on each other that are not the Earth at all. So gravity is more than just the force that holds us to Earth's surface. In reality, gravity is an attracting force between any two objects made of matter, any two objects with mass. And the formula that reflects this is this thing. This formula is referred to as the universal law of gravitation. And next to Newton's laws of motion, this is one of the biggest things Newton gave us. Disclaimer, Newton was not the first person to talk about gravity, but his formulas on gravity did become very famous. What this formula tells us is that the force of gravity between any two things, it doesn't just have to be the Earth, it can be between any two objects, is equal to big G, which I'll get to in a minute, times the two masses multiplied together. So whatever your two objects are, you are multiplying their masses by each other, and then dividing by the distance between the two objects squared. So the factors that affect the gravity between any two objects are the masses of both objects and how far apart they are. These are the two key factors that affect the gravity between any two objects in our universe. This is why, if you were to calculate, your own weight on planet Earth, it's why your mass matters, because your mass affects the gravitational pull from the Earth on you. But what also affects your weight on planet Earth is the mass of the planet, because that's the second object, and also how far you are from Earth's core. That's why, again, your acceleration of gravity and therefore your weight can change if you change your distance from Earth's core. That's why Earth's gravity gets weaker the further away you are from the planet you are. Further away from the planet you are. Even standing on a mountain can change it slightly because you are further from Earth's core. Likewise, if you get closer to Earth's core, if you somehow manage to dig through Earth's crust, note that since radius is on the bottom, if radius becomes bigger, if radius becomes bigger, gravity gets weaker. That's why leaving the planet weakens the gravitational pull. But if r gets smaller, you're dividing by a smaller number, Fg gets bigger. So Earth's gravity gets stronger the closer you are to the core, and that's why the core is perpetually on fire. There's a lot of pressure down there from the vastly increased gravity the closer you are to Earth's core, and that increased weight and pressure keeps at least parts of the middle of the Earth molten. So, just to reiterate again, the two main, gravity can act between any two objects, you and Earth, Moon and Earth, between eraser and golf ball. As long as they're made of matter, they have gravity. And that means you actually have your own gravitational field. It's just not very strong because you do not have the mass of the planet. But you have gravity between any two objects with mass based on said masses and how far apart the objects are. And that is true for any two things. Technically, there's a gravitational pull between you and Pluto right now. It's just really weak because you are very far away from Pluto. How's this feel so far? All right. Now, the Fg here, it's just force of gravity. It's force, it's measured in newtons. The two masses are still measured in kilograms, and radius, which here means just distance between the two objects. It's not like half of that distance, it's the total distance. And we use radius for this because gravitational fields form a circle around the object creating them. So if I was to try to quickly draw Earth and its G field, Earth's gravity is caused by a field that its mass creates, and all mass creates gravitational fields, as it turns out. And so if the moon is sitting here, the distance between the moon's core and the Earth's core is the radius of Earth's gravitational field circle. So that's why we call it R. So the distance between the two objects counts as R for the formula. You don't say take that distance and cut it in half. R is the distance is the radius of this big gravity circle, which conveniently is also the circle the moon forms around the Earth when it's orbiting. So R is measured in meters. It is distance between the centers of the two objects. It is not that distance cut in half. The last variable here is capital G. That is not the same as lowercase g. Lowercase g is negative 9.8 meters per second squared. Capital G is a different constant, and it doesn't really mean anything inherently. What it represents is just the number that has to be put into this formula for it to work. When very smart people were first pondering this, they realized the formula didn't work unless you multiplied the masses by 6.67 times 10 to the negative 11th. It's just a specific constant to make the formula work. It does kind of represent concepts called permittivity and permeability of free space, but that's not something we need to go far into right now. As far as you guys are concerned, big G is just the constant that makes this formula work, and it is always 6.67 times 10 to the negative 11th. That's a freebie, it's on your formula sheet. It's the only time you'll need that number is this formula. Since it's only used in the formula called universal law of gravitation, we just call this the gravitational constant, or universal gravitational constant. Its sole purpose is to make this formula work. So you don't have to memorize it. It's on your formula sheet, just beneath the force of gravity formula that requires it. So that's the only use of an uppercase G in this class. How's the formula feel so far? All right. Now, what's nice about this formula is you can use it to find the force of gravity between literally any two things, as long as you know the mass of both objects and how far apart they are. And again, we use this a lot in space because objects in space tend to have a lot of mass and also usually are very far apart. So, since this stops being true as once you leave the planet, we need a different way to calculate it, and this is that different way. Now, before we apply it to rotation, let's use the formula in a few more mundane examples. First, let us calculate the force of gravity between these two objects. Two 10-gram markers placed 10 centimeters apart. So right now, we are going to calculate the gravity between these two objects. So, brand new formula. Somehow I keep picking up the marker that I meant to set aside as dead. That's because my trash can is missing and can't just throw it away. That's not much better. Fg equals big G times m1 times m2 over r squared. So for our first example, gravity between those two markers right there, they both have a mass of 10 grams and they are a distance of 10 centimeters apart. So let's start plugging things into this formula. Big G, it will always be 6.67 times 10 to the negative 11th. That will always be written on your formula sheet. If you have not gotten a lot of practice putting in scientific notation numbers into your calculator. Make sure that that is something that you can do. I can probably figure out the best ways to do that. I usually use the E button myself. So big G times the mass of both objects. How many kilograms is 10 grams? 0.01, very good. And we have to multiply in both masses. It won't always be the same number, but in this case it's the same number twice since both objects have the same mass. M1 times M2. And on the bottom is radius squared, distance between the two objects squared. They are 10 centimeters apart. How many meters is that? 0.1, very good. So 0.1 squared. Make sure you are only squaring the 0.1. First, any questions in how this was set up? Any issues with where any given number happens to be placed? All right. Now, because of the exponent and because of the square, I will briefly talk about what buttons I would hit on my model calculator to try to do this all in one go. Open parentheses, 6.67. E negative 11. This is calculator shorthand for times 10 to the power of blank. On my calculator, it's actually 2 letter E's, and it's the secondary function of the comma button. If your model is different, I will help you find that button if you haven't used it recently. But whether you're inputting it or if your calculator gives you this as part of an answer, the weird small uppercase E is times 10 to the power of. So this is 6.67 times 10 to the power of negative 11. Then 0.01, 0.01, divide by 0.01 squared, close parentheses. I use those parentheses to make sure only the 0.1 is being squared. Sorry, 0.1. And for all that, how much gravity do we get? Yep. Now in scientific notation, this means very small number. Times 10 to the negative 13th means we take this decimal point and drag it 13 spots to the left. So this number is, this amount of force is so small your human sensory system physically cannot perceive it. This might not even be enough to make the hairs of your arms twitch. And for that reason, you will never see these two markers slowly drift towards each other as a result of gravity, because air resistance is enough to stop them. Besides the fact that they're sitting on a table, and friction from the table is also telling the markers not to move. Yes?
So, in a vacuum with no air, no friction, and they're literally just two floating objects, would they be pulled to each other?
Very slowly, but yes. Over time, in a perfect void, these objects would slowly drift together. And from kind of a very broad cosmic perspective, that's at least some opinions or hypotheses on just how stars and planets form in the first place. Matter that's drifting through space is slowly attracted towards all nearby matter, and eventually, over a long period of time, it will meet and cluster together and keep pulling in more matter until you get stars and planets.
But wouldn't that mean the universe would shrink instead of it constantly expanding?
Yes.
So why constantly expanding instead of doing that?
So this is Big Bang versus Big Crunch,
Okay.
and not part of this class, but I do like talking about space. So just to say, not on the test. The leading hypotheses currently go that the Big Bang was functionally, literally an explosion, and that explosion is still expanding. It's still basically the shockwave part.
Okay.
Like how if you watch real life model test explosions in like science shows and things like that, you'll usually be able to see they involve rapid expansion of something, and that's what creates the boom, is just the expansion, literally forcing a sonic boom as it pushes air out of the way. So there's an expansion, that's why it's called an explosion, it's exploding outward. And we're still in that point. If the universe is still expanding, we're in the kaboom part. But eventually, you stop expanding, and eventually gravity would pull it all back in. That's the big crunch hypothesis. We're still in the bang, and once the expansion stops, comes the crunch.
What would make the expansion stop?
The matter of the universe. I suppose the gravity of the universe eventually slowing everything down. Like if it's all being pulled towards some center point, that gravity would still be there. It's kind of like how you can rise while accelerating down. So basically everything is still being blasted away from the center, but slowing down because gravity is pulling it in. Like it has outward momentum, and gravity is slowing it down, and eventually it will stop and turn around.
Okay.
So everything is currently been blasted away from universal center, as if it was rising but falling, accelerating down, and eventually everything reaches the apex and turns around. And the big crunch is when everything recombines in the center, and who knows what happens then. Maybe another Big Bang. If you watch Futurama, that's the leading hypothesis anyway. Questions? Now, as it relates to this class, rewinding, there's a force of gravity between these two objects. It's incredibly weak, and that's why you don't notice it. Frankly, humans, a lot of humans have a mass somewhere between 50 kilograms to 200 kilograms, which means that most humans have a mass, compared to these markers, of about 0.01 to, let's say, 100. So, 2, 3, 4, 4 zeros bigger. So if we use a human's mass instead of the markers, the answer would only be times 10 to the negative 9. Just 4 zeros bigger. That would be the gravity between me and a marker 10 centimeters apart, which is still not enough to notice. So that is really why you never notice your own gravity. You just don't have enough mass to create a measurable gravitational pull. It's only really when you get on the scale of moons and planets and stars that it starts becoming noticeable. It's also why different planets have different levels of gravity. They just have different masses and different sizes that create different numbers out of this formula. The moon has less mass, less gravity. Mars too. Mars is like a fourth of Earth. Now, again, we can find it between any two objects, so we can actually repeat this to find the gravity between a 75 kilogram human and the planet. This is the approximate mass of the Earth. We don't know that for an absolute fact because we can't exactly put Earth on a scale, but all of our own experimentation indicates that should be the mass of the Earth. And to do that, you would just swap out the mass and radius numbers. Got a 75 kilogram human and a planet with a mass of 5.98 times 10 to the positive 24th kilograms. And our distance between us and the center of the Earth, because it is specifically distance between the centers of the two objects. If you used your distance between you and the surface of the Earth, that'd be 0, and then you're dividing by 0 and the formula stops working. Gravity cares about center of mass, not surface contact. So that's why for radius here, we are going to use the literal radius of the planet. Does that make sense? Again, the R in this formula is the distance between center of mass the center of Earth's mass is the center, the source of its gravitational pull. Same is true for you, actually, but again, your gravity's too weak to really do anything.
So it's still the same thing as like the distance between both objects.
Yeah. It's just very specifically distance between center of mass of each object. But yeah, there are certain parts of physics that treat the object as a point mass at its center, so yes. You can technically treat the Earth as an infinitely small marble right there, meaning you would still be a distance from it. So, for radius, it's not going to be 0 because you're on Earth's surface. It's going to be 6,378.1 kilometers, but we need that in meters. And then, once in meters, that big number needs to be squared. So how much force does this give you?
I have 735.37.
Yep. I'm going to cut that at 0.4, but that is what I got as well. Does anyone disagree? So that would be the weight of a 75 kilogram person on planet Earth. Let's compare that to the old-fashioned way that we would find the weight of a person on planet Earth. Fg equals m times g. 75 times 9.8. Hey, look at that. Secretly, or not secretly, I'm telling you, this 9.8 was derived from this formula. Basically, if you just rip the 75 out of this, if you just multiply g times Earth mass over Earth radius squared, so not factoring in the 75, big G times Earth mass over Earth's radius squared is 9.8. That 9.8 comes from a variation of this formula. And so you can kind of do that on any planet. You can find the acceleration of gravity on a planet if you know its mass and radius. You do it to the moon too, and the moon is like 1/16 Earth's gravity.
I keep getting 73,000 when I put it in.
73,000?
Yeah, for some reason. Is that like a calculator thing with that?
Maybe.
Did you square?
Yeah, I squared it.
I got 9.8.
I'd have to look at your work.
Might be the exponents.
Maybe. And again, calculators are weird. Calculators are kind of dumb. So it's likely not your fault. It's the machine acting up. Any other questions about this particular example for the time being? Okay. So, in physics, we like this formula because we can use it for any two things, including planets that are very far apart from each other. Which means, finally, you know what, let me rewrite this slightly. I'll make it a little more obvious the steps we're going to take both ways. So, let us now figure out the force of gravity between the Earth, pardon, and the Moon. It will be pretty similar to the version we just did. We need big G, the mass of the Earth, but instead of the mass of the human and the radius of the Earth, we need the mass of the Moon and the distance between the center of the Earth and the center of the Moon. So, Earth's mass is still going to be 5.98 times 10 to the 24th kilograms. The approximate mass of the Moon is 7.36 times 10 to the 22nd. So it's got 2 less zeros than Earth does, which you might not think is a big difference, but that by itself could reduce the gravity by 100 times with no other context. You have 100 times less mass, you have 100 times less gravity. But because we're about to multiply two very big numbers together, we're likely to get a very big answer. Lastly, on the bottom, the two objects are approximately 384,000 kilometers apart. Once again, we like meters as a standard unit in here, so we have to multiply that number by 1,000 to turn it into meters, and then we square it. So this entire equation is very extreme numbers. But it's still big G times mass 1 times mass 2 divided by distance between the two objects squared. And what sorts of numbers do we get?
1.99 times 10 to the 20th.
Thank you.
Oh, yes, I need it too.
Can you repeat that? Sorry.
1.99, 10 to the 20.
Oh. Turns out I made a mistake. So you guys are checking my work today. Thank you, by the way. There it is. Yes, you guys are absolutely right. Force of gravity between Earth and Moon is 1.99 times 10 to the 20th newtons. This is more force than you will ever feel in your life, because if that force was acting on your body, you would be immediately reduced to the flattest pancake in the world. But something important that I want you to take away from this, there is gravity in space. Earth's gravity does not turn off once you leave the planet. In fact, it's there and it's still very strong. It just gets weaker the further you are from the planet. If the moon was on Earth's surface, this number would be huge and it would destroy the Earth. But there is gravity in space. The astronauts on the space station are not weightless, they are just perpetually falling because they are in centripetal orbit. They are not weightless, they're just falling. Turns out the actual gravitational pull in orbit is like 9/10 what it is on the surface. It does not actually get that much weaker until you leave the until you leave Earth's vicinity completely. So, very big force acting on the moon. I will point out likewise, the moon does this to Earth as well. This number is inward on both sides. Earth pulls in on moon, moon pulls in on Earth. The moon is also attracting the Earth towards it the Earth is just so big that its acceleration because of this force is negligible. Meanwhile, this force is bigger, well, comparable to the mass of the moon, so it causes a more measured acceleration. All moons, if pull on their planets, it's just if the planet is big enough, it doesn't affect its motion. This is one reason why Pluto isn't a planet anymore. More on that later if you care.
I thought they made
I
it a
thought they,
planet
yeah,
again. What?
yeah.
Did I miss a science journal? Sounds like I have some research to do.
They changed it back
Really?
recently.
Okay. I will happily research that because I'm fascinated. Apparently I missed some science news. That's on me. I want to demonstrate though that we can use this as a centripetal force. This force of gravity is what acts as a centripetal force on the moon, causing it to orbit. So in space, this formula is often paired with the centripetal force formula in order to calculate orbits. So this number we just found is the centripetal force acting on the moon. Therefore, we can set that force equal to the centripetal force formula, mass moon times velocity moon over the distance between Earth and moon squared. And we can figure out the speed of the moon. It's very fast, spoiler alert. The moon is moving very fast. I'll try to do that very quickly. It's Friday and I don't want to hold you up. 1.99 times 10 to the 20th, you may begin packing up if you wish. Mass of the moon is very big. Velocity squared over that same distance. The distance between the two objects will be changed. Times 384 divided by 7. The velocity of the moon in meters per second is 1,018, which is at least 3 times the speed of sound, or about 3 times the speed of sound. Let me know if you need anything. Work on chapter 7 homework over the weekend, and have a great weekend.
I'll just yeah, awkward.
Dr. Hoffbauer, what chapters will be on the next
I
one?
will, I have work
6
and,
through 9.
but I can't do.
6 is momentum, 7 and 8 are rotation, 9 is pressure and buoyancy.
Probably was me after Monday though. But I'll send you videos while we're working. This is my time.
Yes, I plan
That's
on
nice.
emailing it out today. What I'm gonna do is,
On top with the
I'm basically gonna slightly tweak the in-person version and give you sample numbers. Just rewrite the instructions to make everyone clear what's going on. And so I just needed to grab some sample numbers today to put on there for you to use. So that'll go out this I will send you that this afternoon once I finish putting the numbers in.
Okay, thank you.
Welcome.
Anything